like how a particular client is, whenever a client is going to make a request. So basically, either it is going for the storage or it is going for the processing. So first, if the storage is not there, so the client first, it has to write the read to HDFS, then it will go to the name node, and if it is for the processing, so it will go to the resource manager, and based on that one, either the node manager will talk to data node, or data node is going to talk to node manager. So this relationship we have already seen, like masters can talk to each other and the slaves can talk to each other. We have also seen this federation architecture, right? Then we have also talked about this high availability architecture. Then how this resource negotiator yarn is basically negotiating with the resource manager to process any of the processing file request the client itself. So this process we have also talked about. This thing, this was just for the so basically, if although we are not going to do this, but just to give you a information that okay, how we should generally when we were working with the Hadoop system. So generally we used to have the different cluster modes were there. One is standalone local mode where as I told you, there were 4 daemons were there. One is my name node, then data node, resource manager, and node manager. These are the 4 minimum daemons should be required to run whenever we are going to work on a Hadoop cluster. But if we have to work on let's say I'm working on a single machine, my local machine, so there basically no daemons are working, as we are working on a single JVM. So basically, let's say if I'm working on my own system, so here we don't have we are not going to have different machines are there, everything is happening on a single machine. So it is just going to be work as a standalone or local mode. So if whenever I have started let's say just for practicing, or what if I don't need to make a cluster out of it, so I can work with this standalone mode. So it is mainly for running MapReduce programs whenever we are doing some sort of development just for the testing purpose and all, like whether we are able to process the data or not. Another mode that we generally use even when we are working in a organization itself. So let's say if I have to work on my local machine first, and once I am confirmed that okay, this thing is working fine, then I move to the the another fully distributed mode. So pseudo distributed mode is also the same as my local mode, as I'm working everything in my local machine. But pseudo distributed mode, what it does is basically all the daemons are working on the same machine, although like the replication and all, whatever we have set as the default one, those are going to be set on the local machine itself. Like if I've set it as, let's say default replication factor was 3, so for the same same file is going to be copied to my machine locally to 3 different folders, but there is no use of it. So what we generally do is, like when we are working in the pseudo distributed mode, we generally used to have only one replication, not more than one. And then finally, which comes as the fully distributed mode, is the actual mode where we actually run our cluster on the production environment, or even in the organization. So we generally work with this fully distributed mode. But in organizations also, like if you are testing anything on your local machine, so there we are going to use this pseudo distributed mode, where everything is running, all the daemons are running on the same machine. But in fully distributed mode, what happens is, like on your machine, like name node and resource manager, they are going to be running on a dedicated server, and other data data nodes or the node managers, those are working on my cluster of machines. So this is the actual difference, correct? So these are some of the the commands, basically Hadoop commands we generally when we used to use it. So as of now, there's no use of it because we are not going to work on any of the Hadoop shells as of now, because when we are going to do the hands-on, everything we have to do it on the PySpark itself, either in Python or PySpark, right? So that's why. But if we, even in there itself, we want to use these, because in background this is running. So if we want to list the files through HDFS, DFS, that we can do, right? So as I told you earlier, like everything in Hadoop is going. We are going to develop it through some configuration files. So these are some of the the main configuration files we generally used to have when we are working with Hadoop system. So Hadoop environment env.sh. So this is one of the uh, file which basically contains all the environment variables that are mainly going to use whenever we have to run the Hadoop. We are going to run the Hadoop ecosystem. Then core site.xml. This is one of the important core configuration file setting is there, where we have to implement, or we are defining all the input output settings, like what going to be for HDFS and MapReduce, like what is going to be my the file path is going to be there, where my name node is going to be reside. So those kind of things that we have to specify. Then HDFS site.xml, again this is for all the my HDFS daemons. What will be my name node, what will be the name of my secondary name node, where it is going to be reside. Those kind of settings are going to be part of my HDFS. So all the HDFS means Hadoop distributed file system. So wherever it comes to the storage part, these are going to be the this is going to be the file where we have to put all those configurations. MapRed means wherever it's going for settings for the MapReduce applications. So which basically the you can put which particular library we are going to use to to call this MapReduce files, which mean files are going to be there, libraries are going to be there, those settings are going to be part of MapRed. Then yarn site.xml basically for resource manager and node manager. And then in masters, we are going to have a list of all these secondary name nodes. But generally, basically, as a part of masters, we generally used to have only one secondary name node, because my name node, active name node, and the standby name node, those are reside at the same point of time. So here, generally, if you want, generally there is only one secondary name node used to happen, because in Hadoop 2.0, as I told you, the concept of standby name node came into picture, which generally doesn't going to be use this secondary name node, because secondary name node here acting as a cold backup, because for hot backup we are already having this standby name node, because whenever my name node is down at the same point of time, without a fraction of seconds, this standby name node come and act as an active name node. And within the slaves itself, we are going to have all the data nodes and node managers are specified. So slave all my data nodes, or we can say commodity, the hardware that we have, machines configurations. So core site.xml, HDFS, we have already discussed. So if you see, like what is going to be my default file system, like so this is my for localhost, but in fully distributed mode, this is actually going to be the my my server address, where my system default file system resides. Similar way, HDFS site.xml. So as I told you, here we are going to define what is going to be my replication, what will be my unit AFF permissions, name node directories, data node directory. So these where my actual files, my name node resides, those kind of information resides in HDFS. Then on which framework my MapReduce works, it's Yarn. So this is not the only, the settings that, but these are few of the, the main settings we generally use. But apart from this, we have got lot more settings are there, which should be the part of this, these. Okay. We discuss this thing, and yeah. So these are some of the default ports where these services generally runs. Name node generally runs like if you are going to run. So by default it is 512.0.70, data node 512.0.75, resource manager 808.88, node manager 8042. And if you want to work for, you want to see where the job history is going to be run. So if you want, you can get this statement. MapReduce jobs. So that is part of this particular daemon. So if you whenever we are going to see the process HDFS DFS -ps, if we do this, so if these 4 or 5 actually this job history server is not exactly required, but these 4 daemons should always be up and running, then only we can perform our read and write operations. If any of these 4 daemons is missing, then we would not be able to perform any of our read and write operations, right? So yeah, this was so generally previously we also used to have this pig, but now it's obsolete. We are not using at all. But yeah, in some of the organizations still we are using it also. So as I told you earlier also, Vineet, there is a lot of noises coming from your side. Can you just mute yourself?
Raj, you're not audible.
Hello, am I audible?
Yes.
Okay, this is, but okay. I thought like I mute Vineet, but I have muted myself. No worries. Okay. So what I was telling is like here itself, as earlier also I told you, like to move the data from to HDFS, we generally use either using Hadoop copy commands. We use Scoop or Flume. Hadoop copy commands can move our data, whether it is going to be structured or unstructured data sets to HDFS. But if we have to move only working our data set from directly from let's say from some data warehouse database directly to HDFS, so we can use Scoop because it is only used for moving the structured data set. Then Flume is mainly for the unstructured data sets. Once my data is there in the HDFS, that we can process it. So either we are going to use MapReduce. If we are not using MapReduce, so there were another tools are there like Hive. I don't know. Some of still companies are still using Hive. Those who are still working on like generally the banking domains, which are still working on some mainframes, right? Mainframe systems. So they are still using Hive for data analysis, but Pig now it's not in use because I've never like in I think last 5-6 years. I've never encountered someone who is using pig. But pig is again data analysis language. It's like a English like language. We just need to put some English statements and that. But in background, everything in Hadoop, as I told you, it is written in the MapReduce itself. So whatever I'm specifying as a part of pig or hive, that is internally getting converted into MapReduce, and that is getting processed itself, right?
Oh, will you show how pig works and how hive works?
Can you come again? Your voice is.
No. Will you show in future that how we use the pig and how we use the hive?
If you want, I can show you. But for that, basically, we need to install this CDH, or else we have to create, install Hadoop and everything. Instead of that, we are having one, CDH is there. But if you want like a Hive, I can show you. So using like how Hive works. Hive is similar to the sequels. So I can show that to you online itself. Like I think we can get some.
Okay, so
online
what we are going to do, what we are going to use instead of hive and pig?
So basically, once we are done with these, core concepts, so we'll move to PySpark, and there we are going to use, we are processing everything either using PySpark or SQL, and mainly we will be working on Databricks, because Databricks is a unified platform where you will see all these things integrated in a single environment. Apart from this, we are also going to work on ADF, that is Azure Data Factory. So yeah, those services we are mainly going to work upon. But we are going to use those, so internally these things works. Like Hadoop is still getting used. Now we are using clouds are used. We are using for storage. But some companies, they are not using cloud, so they are storing their data sets still in the form of HDFS, right? That's why we have to know, and it's still, I must say, like not. I'm not sure.
No.
But, it's 10% of the companies are still, they are working on Hadoop technologies, but not more than.
Yeah, I hear this hive. I hear this terminology hive somewhere. So
yeah, Hive is still getting used. That's what I'm saying. Like Hive, like wherever in banking domains, still some of the organizations, they are still using Hive. Like one of my colleague he's in US and he's in TCS. Still, he used to work in Hive itself. Like still he used Hive. Yeah, so there are some because still they are working on mainframes. So most of the, apart from banking, and in banking also, it's not more than 30 to 40% people, organizations are there. Those who have not moved to the new technologies, but maybe in future they have to move to this one. But Hive is it's almost, if you know SQL, then Hive is very easy. And I believe like you have already done with this SQL Python, right? Or
yes, yes.
Yeah, then that's good.
SQL, how far the comments are needed, I don't know in here. So, but I know basic, like the real.
So like CRUD statements about apart from this, using joins, CTs, and window functions.
Yeah, joins and window functions as well, I know.
Yeah, so basically these are the main things, like like you should know how to use window functions, how to apply those window functions, how to where we have to apply which join, and group by having. These are the some of the important things that in most of the cases we have to use. Apart from this, that's usual that we generally use. So it's all depends on the complexity. But if somebody is going to ask, so mainly the questions are going to be asked from these topics only.
Okay.
Yeah. So yeah, this is just to copy the put is basically to move the data from your local to HDFS, and the copy from local means your it's the same command that put is doing, right? Either you can use put or copy from local, and again get and copy to local. So whenever you want to bring something back from HDFS to your local system, right? So there we are going to use HD Hadoop, or either we can use Hadoop DFS or we can use HDFS DFS hyphen put, and this is my file, and this is going to be my target. So this weather.txt file is going to be moved to this HDFS location.
Okay.
It's not, again, this distributed copy is basically used whenever we are going to use for, we are moving the data between the clusters, like from one, one cluster to the another cluster. There we have to specify the actual path of my clusters. And this is generally used for, data recovery. If something went wrong, then we lost some data. So generally we used to have the data at different locations. We can move the data from one location to the other location using this CP copy, very distributed copy. But nowadays these these things are being done by the admins itself, like distributed whenever your lays lost the data. And this is very rare chance that that if something happens very rarely, then generally it happens to go like this way. Otherwise this doesn't happen very easily. So this is how we can use Flume. Flume, as I told you, it is mainly used for moving the structured data set. So this is one example given by the from the Twitter itself. Like Twitter, basically, the streams are getting, so Twitter, people's tweeting on Twitter online now, it's access there. So on runtime, if you want to analyze those things, right? So for that we can use Flume. So what we generally used to have is in most of the data ingestions, we are having source and sink, right? Or sometimes we are saying source and target. So if I'm saying source and sink, source or target, source and destination, so sink, target, destination, is these are all same things, right? So source is going to be my Twitter, and channel is going to be like because Flume is going to store these tweets in its memory, and then finally storing it to the sink, which is going to be stored as into the HDFS section, and then we can process it, right? Okay. So let me add another. Okay, so we have already discussed this thing. Same. So now they are going to very some easy questions are going to be there, just to rewind what we have done so far. So what will be the answer for this? Sharmila, am I audible? Hello.
Oh, am I audible? Sorry, I was on mute. Yeah,
Oh,
tell me, Raj. Yeah.
is this statement true or false?
What? Ask again.
Are you not able to see this?
No, I don't see any. Your screen is not shared. Not shared yet.
Now it is visible.
Not clear.
Now?
Yes.
Okay. So secondary name node is a hot backup for name node. Just true or false?
Secondary name node.
Just remember the concept I told you.
Secondary name node is hot backup for name node. Name node. Name node is the master one, right?
Yes. No.
The
Secondary name node is also master. But my name node is active, right?
hot backup. Okay, yeah, yes, true. Then if that node fails, the second it takes the secondary name node, right?
Okay. And what about the standby name node?
Oh, oh, secondary name node and standby name node are not same.
Yes. So generally we got confused with this, right?
Yeah, it sounds similar. Yeah.
Yeah, it's a standby name node, which is the hot backup.
Okay.
Secondary name node is a cold backup. And even in 2.0, Hadoop 2.0, it is optional. It is not mandatory that we have to keep it secondary name node or not.
Okay. Oh,
You see?
false. Mm-hmm.
Now, how we generally used to resolve the problem, solve the problem in traditional way. So when we have got very huge amount of data, so we generally used to split. We used to split it using some sort of our commands. We used to
Mm-hmm.
split the data, and then we are going to apply some sort of grep statements on top of it to match the data. And finally, once we have got the match, we used to combine that data using concatenation and finally finding out all the matches, right?
Okay.
When we are working on, let's say some GBs of data, this was fine. But when it goes to, in terabytes of data, so this process becomes quite, you know, tough and complex, because every time you're going to split it, then applying, and these things are going to be how much parallel
Yes.
we can achieve on a single machine. It was very difficult to, even though there was the concept of, uh, multi-threading, but how many multiple threads are going to be run at the same point of time, that was an issue. So, but how we are going to do it in the MapReduce ways, when we are going to have, very huge amount of data is there. So within this MapReduce framework, what we have done is only we have to write the code for this, mapper and reducer. This splitting of the data is automatically going to be done by the framework itself. Because as I told you, by default, what is the What is the block size that we are having? What is the block size?
Size. Remember.
Remember all these things, right? Because these are the things that we in interviews. This question can be asked, like, what is the default block size? Still, we are using this 128 MB, right? So let's say my file size is 1 GB. So 1 GB divided by 128, 1024 divided by 28 MB. So it is coming out to be. So basically, my data is split into 8 bits, and then we are going to apply the mapper function on top of which. What the map does is, map is going to break it into in the form of key value pair, because my map only understand data in the form of key value pair. So whatever the data that we are getting, it is going to convert it into key comma value, and then once we are going to get the output of the mapper is also going to give you output in the form of key value pair. So map takes the input in the form of key value pair and also gives output in the form of key value pair. So once we got the output of the mapper, the reducer's work is to reduce, means it is going to combine the data, whatever it got from the mapper, and give the result to O. So because of this MapReduce framework, the data that we are getting, either it's going to be in terabytes or petabytes, as we are working on a cluster of machines, right? So this mapper and reducer are running in parallel on multiple machines. So because of this, whatever the task we generally takes, if we talk about in traditional way, it was taking, let's say, 24 hours to process the data. Using MapReduce, we can do it in just 30 minutes of time, right? Or even less, or it can take, let's say, hour based on the the cluster size, right? But we are able to reduce our time a lot, right?
Okay.
So what my mapper takes? My mapper takes input in the form of key value pair and also gives output in the form of key value pair. And reducer also takes my data in the form of key value pair and returns the data again in the form of key value pair, right? So both my reducer and mapper takes data in the form of key value pair, right? Okay. So why we are using this MapReduce?
So you asked me that what is the size of block? Block. Okay, each block is of 128.
Yeah, by
GB.
default in Hadoop, even in if we are using any of the cloud technologies, if we are using any, let's say we are using S3 or ADLS Gen 2, or we are using Google Cloud Storage, any of the any of the cloud, their default storage size is 128 MB, right?
Okay.
But if you want, you can make it to change it, but generally it's 128 MB. So it's now become a very standard one.
Okay.
So now why we are using MapReduce? It has got two biggest advantages. Like, we are taking processing to the data. First thing is, like, we are not moving our data. Wherever my data is there, we are we are making available processing on the same machine, right?
Okay.
Got it? And another one is processing data in parallel, and we are processing the whole data in parallel. Now, how it is going to be done? As I told you, we are having the rack, replication factors are there, right? Last time we saw. So let's suppose this is my first, first use case is there. Let's say wherever my data is there on the same HDFS block, I am processing my data on the same machine. So this is this used to call as my data local. Like wherever is my data is there, I am processing from the same machine, right? So my data is this is my block, HDFS block, and this is my processing. So I'm processing on the same block of data or on the same machine, right? This is my rack. So within the rack, I have got multiple machines are there, right?
Okay, standalone.
Yeah. So this is going to be my data local, like wherever my data was there, and this is going to be the fastest one, right?
Oh, yeah.
Yeah, because wherever my data is there, if I'm processing from the same machine, it is going to be the fastest one. Another one is, it might be the case like wherever my data was there, so this machine was not available. Like this on this particular machine, on this machine, the name node, and I'm saying node manager, right? So node manager is not available on this machine. It was busy in processing other tasks, right? It might be the case, right? This can be possible that the node manager on this machine, because as I already told you, on each of these machines, we have got data node and node manager, because these are the slave machines, commodity hardware. Right? On every machine, we are having node manager and data node. So this might be the case that this on this machine, this node manager is not available. Then what is going to happen if this is not available? Then we'll try to process, but it might be the case that it is available on another machine, this machine, this machine, this machine, but with the same rack itself, right? So like this way. So my data was on this machine, but my available node manager was on this machine. So we are processing from this one, right? So this is called rack local. This is data local. We are calling as data local. This is rack local. My handwriting is very poor, right?
That's fine. You can write a DLRL, that's fine.
Yeah. So this is rack local. And if this is also not, and this is going to be case when we are dealing with, very huge amount of data and very, like all the machines are quite busy within this rack itself, then we can take the help from the nearest rack. So this is going to be the third case. And this is called as off rack mechanism. OR. So this is going to be the fastest. It will provide the fastest results. But if data locality is not available, then it will go to the rack local, otherwise off rack mechanism, right? But in any of the cases, your data is going to be processed in parallel at the same point of time, right? So this is how it works. Okay, so this is how we generally used to, let's say, an example has been given. Let's say, through Scoop, we have loaded some data to the HDFS, and then from HDFS we are reading it this CSV files into mapper function, then applying. So map is taking the data in the form of key value pair, then producing the output in the key value pair, and this mapper's output will go to the reducer as input, and the reducer is finally producing the output, which is again going to be stored in the HDFS, and then it will be sent back to the client itself, right? So this is generally what we actually do in our day-to-day life.
Okay, after the reduce is done and it goes to the HDFS and then it moves to client.
No, basically what happens is, like, let me give you this is how basically the whole process works, right?
Okay.
See, this is my client. So client can be my local machine. Let's say from my machine, I'm just giving one command that, okay, if the data is already there in HDFS, so I'm going to, I need to process it. And let's say my data is, let's say 100 GBs of data, or let's say 500 GBs of data is already there on the cluster. So I need to process, or I need to do some sort of analysis. And for that analysis, I have already written my code, right? And that code can be in Hive, code can be in Python, that code can be in, PySpark, SQL. It can be anything, because if I'm talking about Hadoop, so Hadoop can also, you can write the code in Python, Scala, R, and SQL. Basically, Hadoop doesn't support SQL, but these three ones, and R also. But now our latest, machines, the applications that we are going to work, they also support SQL. So because of this support of SQL, and why this, as I told you, Hive was introduced, because the people who were working on the, basically on the data side, they were mainly from the SQL background, right? So when this MapReduce came, so MapReduce was originally written in Java. So to adapt to Java for the people who were mainly have got the background in SQL, it was very difficult for them to work on those things. So what they did is, like, for at least for those people who are working in structured or semi-structured data sets, they have built this new language called Hive, right? So Hive is generally used for data process analysis part, and uh, where the code was almost similar to SQL. So at that point of time, basically Hive was a very good you can say processing analysis tool was there, which really helped a lot of people to analyze their data and process their huge amount of data, right? So here what we are going to do is, let's say client has made a request. So if the request is made for storage, so it will go to name node, right? And if it has to go to the request for a processing, so it will go to the resource manager, right? Even because name node has got all the details about, even when the resource the client is asking for a, let's say I have a file, let's say abc.txt file, which contains, let's say, some I'm just taking very basic example. Let's say I've got some words are there in a file, let's say a file which is having a lot of lines of text is there. So I want to count the occurrence of each word in that particular file. Let's say, hi, how are you, how are you doing, what's your name, like this. So hi, how many times it has been appeared, hi, how are you doing, how's, likewise. So I have a file and I need to count the total occurrence of each word in that file. So basically that file is already there in HDFS, and where that file is residing, that is this particular name node is having all the information about this, because name node contains the metadata, right? When name node contains metadata, so metadata is data about the data. So what this, let's say I'm having a file called abc.text file, and that contains some files are there, some files which contains a lot of text is there. So we want to count those occurrence of each that file. So the resource manager doesn't know where this abc file is existing, right? So who knows this? Who knows where this file abc.txt file existing?
Name node.
Name node. But as resource manager is a master service and a name node is a master service, they can talk to each other. So this resource manager will go to name node and will ask, like, okay, I need to process this abc dot file. Kindly give me the location of this file. So basically, in return, this name node returns a metadata about this abc file. So it says like machine 1 is on this one, machine 2 at this location, machine 3 likewise. So it gives, then this resource manager, now it knows, and their applications also, like this file fun is 1, 3, 5, and 6. Likewise, file 2 is existing at this location, file 3 is at this machine, right? Then this resource manager sends this, after getting this information, it sends talk to these node managers. Now resource manager can talk to different node managers. So wherever this particular abc.txt file is existing, ask them to process this particular file. So although I am having multiple replications are there, like my processing only happens on a single machine, right? Understood? I have got two applications, but my processing only happens on one machine. My processing is not going to happen on multiple machines, right?
Yeah.
So it does is resource manager sends to node manager, and the node manager processes it. Once it processes it, process got completed, then it sends results back to the resource manager, and resource manager back sends results to the client itself. In this way it works. Now, what it comes is, like within the node manager itself, we are having the containers, which actually performs the task. So those tasks are going to be, distributed to this application master by the node manager. So this application master is one per job. So let's say this was my one job. I have to process this abc.txt file. So one application master is going to be created on any of the node manager, and this application master is going to connect to all the node managers wherever this particular, let's say I have 1 GB, right? So 1 GB file is there. So with 128 MB, how many number of blocks will be there? 8. And its replications with 24. But my processing is going to happen only on 8. So this application master is going to process or talk to all the node managers wherever these 8 processing are happening. So those can be happen on different machines, or those can be happen on 2, 3, 4, 5, 6 machines, wherever it is applicable, right? So once this task is going to be completed, results goes back results to the node managers, and node manager will send back to the resource manager send back to the client itself. Now, this was the case like where it is done perfectly. There was no failure. But as I told you, we are working on which? We are working on commodity hardware. So there can be the cases that my job got failed. And in both the cases, like when I'm writing the data or when I'm processing it. So there are two ways. So when I'm processing it, I'm telling you first, like when we are processing it. So if on this is going to be application master is going to be one per task, right? One per task. And for each mapper task, like on different machines, my mapper task is going to be consumed. So there we have got one app master is there. So app master is going to be one per task. So that app master always, or this we can say, this node manager gives heartbeat every 3 seconds. Every 3 seconds, this node manager gives heartbeat to this resource manager that okay, I'm fine, I'm working. Like if for a specific amount of heartbeats, if resource manager doesn't get any heartbeat from any of the node managers, then the resource manager thinks that this particular node manager is not working. So the same task on which this node manager was working will be assigned to some other node manager, because it already has got the metadata. Okay, like this one file was working on 1, 3, and 5. So if one is not working, so it will assign it to third machine number 3 itself, right? So in this way it works. Similar goes to the when we are writing the data. So for writing the data, like name node first checks, okay, like client says, I want to store this 1 GB file onto this cluster. So it will go to the name node, and name node checks, because name node has got the idea. Okay, on my machine, how many number of nodes are there, data nodes on each data node, how many data has been written, where we can write the data. So based on that, name nodes sends, uh, based on the availability, name node sends those files to the node manager, data node, sorry. Because first we are going to use the data nodes. Halaki, all node manager and data node, they are on the same machine, right? They are working on the same machine. But the data node, we are specifying when we are talking about storage, and name node manager we are specifying when we are talking about processing. Because what they are only the threads, daemons. Daemon means threads, right? So these are the threads which are working on these machines. So in the same way, when my original, files I have written, let's say 1 GB file was there, initial 8 mappers I have written, 8 of data I have written. So for replication, as I told you, if it is each data node can talk to each other, they try to replicate the data to the nearest available machine because of the bandwidth network. So the machine which is going to be the closest one is going to, it has to replicate the data, then it will be faster, right? So they always try to write the data to the nearest machine, right? So in this way, this process happens. Understood how the read and write process happens? So in the same way, when we have written the data, the processing is also going to happen in the same way, right? Now, this is how the MapReduce, basically, these are the components of MapReduce and how they work. So as I told you, client is the one who is going to submit the MapReduce job. To whom it has to submit? The resource manager, because it's going to be at the cluster level. Resource manager is there, which has got it, as it is working on the very high-end machine. So it is having very high quality hardware. So it's going to be long life. It's not going to be down very easily. Node manager, they are one per data node. On each data node, we are having one node manager, and they are mainly for the monitoring the resources on each data node. Then job its server, basically to maintain all the jobs that we have submitted onto the cluster. It maintains all those things. Then application master. It is one per application. It's short life because whenever my jobs finishes, it automatically kills itself, and it also coordinates and manages to MapReduce jobs with all the different node managers, and it also negotiates with resource manager to schedule the task. Then containers are the main, you can say threads where actually my MapReduce tasks are getting executed. Here we are actually having all the resources in terms of memory, CPU, what is the storage is there. So those kind of things are going to be the part of my container itself, where my actual processing is going to be happen. Let's say I have divided my job into 1 GB data to process. So all those 8 blocks of data is going to be processed using these containers itself, right?
Okay.
So this is how it happens. My job submission is there, then job initiation, task assignment, memory management, status updates, and if there are going to be any failure, then failure recovery is going to be there. So this is how my job executes. So I'm going to tell you step by step how it works, right? So first thing, as I told you, my client is there. It is this client is going to make a request for the job run. So this is going to be a first step. To whom it has to make the request, it will go to the resource manager. Now, once it goes to the resource manager, so resource manager creates a new job ID, right? Once it creates a job ID, or it's called job object, then this job object basically gets copy all the job resources. Now, what are job resources from the HDFS? As I told you, like we have gone through these, core site.xml, HDFS, all those files. So apart from this, any jars, any libraries which are required, those we already specify in the form of our mapper and reducer code. So those things it will acquire from the HDFS itself, because those are already there in my HDFS, right? I have copied those sources in the HDFS. So from there itself, it copy all those resources and then it submit it to the resource manager. So once these resources are available with the resource manager, then the resource manager next what it is going to do is it is going to start the application master. Now, once this job got submitted, once we have submitted the jobs, when the job is going to send it, when this job object get these job resources and submit it to the resource manager. So after submission to the resource manager starts the application master, because as I told, this application master is one per application, right? So sorry. So once this source manager submits the application master, then this app master goes to this node manager, because where my processing is going to happen on the node manager itself, and this app master goes and creates the containers. It's called app master. Basically, this start MR app master is this is basically not the app master. This is wrong actually. This one. This is little confusing, but this is application master, not the app master, right? So don't get confused. This is application master.
Okay.
App master and application master are different, right? App master is going to be one per container. For each container, there is going to be one app master. But this application master is going to be one for full application, right? So this creates the container. Then once this container creates then this app master, how it is going to work? So for that thing, it needs to get those input splits, right? It has to get, now there is one more thing, block and input split. Now we were talking about block, right? The block is my physical data. But when we are processing it, we call it as input split. I'll tell you what is the difference between, this question can also be asked, what is the difference between block and input split, right? For now, you can take it as block and input splits are same. When my block is going to be the part of in RAM, when we are moving this block of data into RAM, we are calling it as input split, right? Because where my processing is going to happen, my process is always going to happen in the RAM itself. So these input splits or blocks are going to be the part of in the form of CPU or RAM, where my actual processing is going to happen. Once these app masters are going to get these input splits, let's say for our one there are going to be 8 splits are going to be there. Okay, so acquiring those input splits, it is going to perform the data. Once this is done, then it is also requesting for the resources, because the resources are already, these resources are already there with my resource manager, right? Third step, these jars or my MapReduce code has already been copied to the resource manager. Then resource manager sends these resources to each of my app master, right? Then in the next step, these containers, this once after getting these resources, this node manager is going to create the actual containers where my job is going to execute in the form of JVM. That is, 8 containers are going to be created on different node managers, and they will execute those tasks of mapper and reducer task. And finally, once that has been done, then my final result will be return back to my client, right? So this is how it happens. The same, it has been given in just one, full, that MapReduce client is creating a job request. Then resource manager creates a new job application. Then this job object is going to get the resources from the HDFS itself, and once it submits the job application. Then resource manager is going to start the container on each of the node managers, and this node manager launches this app master, which is going to coordinate with all the node managers. This is basically going to initialize the job and retrieve all the input splits. Once it got retrieve all those things, then it is going to start all the containers on different node managers to launch this MapReduce task. And once it completes, then it is going to return back the result to my client itself. So this is whole process, how it processes my data, right? Now, as I told you, like multiple tasks are going to be running, so this is what I have shown you, just work for one client, but we can have multiple clients are going to be there. So just to show you, there are two different, color formats it had been given. So one, different clients are going to send their request to the resource manager. Resource manager then sends those requests to the node managers, where my actual processing is going to happen, right? So for this, we are going to, these app masters are there, which are basically going to process their data onto different containers. Once they finish it, send back result to the resource manager. Resource manager send back results to my client. So this client can be on my standalone machine, or it can be on my driver node. And we used to call it as driver node. We are going to talk about this part, right? But the concept is similar, because here also we are having the master slave architecture is there, and in Spark also we are having the same master slave architecture, right? So we have got masters are there, and we are also having the slaves. So resource manager to node manager to app master to containers in the form of MapReduce. We have already talked about this. Let's say this is my applications master. As I told you, applications manager is the one who is working at the resource manager, and this app master is the one who is working at the node manager level. So this app master one is working on these two node managers. This app master 2 is working on these three. So based on the the number of applications that we are running, we can perform these tasks in parallel. So these are some of the the failures, how the fault tolerance is going to work. Like if my task is failed, so basically it's going to be that task is going to be assigned to someone else. But if my if anything fails at the application master level, so like if my application master is failed, that means the job is failed. So it can be controlled by yarn dot. So here we generally used to put some sort of retries. So if default is here, it has been given one, but we generally used to have 3 retries are there. So if within 3 retries it doesn't work, because sometimes what happens is there, like sometimes we are short of some resources. So if it is asking for resources at that point of time, all the resources are not available, so it can fail. But let's say if it is doing for a retry at that point of time, some resources are available, so it can pick up those resources and it should be able to do that. And if my node manager is failed, so I have already told you, like if there are no heartbeats from the node manager to resource manager, for let's say this is an example given for 10 minutes, but it doesn't happen for that much amount of time, because our jobs generally doesn't take that much of time. It generally goes for, let's say maximum of three like for my use case, we generally used to have it maximum of 3 minutes. So for maximum 3 minutes, if source manager doesn't have any node manager heartbeats coming, then generally the that resource manager assigns the same task to some another node manager, right? But what happens if my resource manager is failed? So as I told you, resource manager is failed is going to be very less, like very rare, because it's working on the very high end machine. So generally, resource manager or node manager are going to be failed if my, let's say, name node is down. If my name node or resource manager as both are working on the same machine, so we have got the concept of high availability architecture. That is, so standby name node is there, right? So that's why it's quite it is very rare that, okay, if your main name node is down, right, and it has switched to the standby name node at the same point of time, my standby name node is also down. But I have never seen these kind of scenarios, because these are very high end machines are there. So very high end architecture is there, very expensive machines we generally use as a part of master. So those are not going to be down very easily. So that's why we only have the concept of one standby name node. But yeah, where the availability required to be 100%. So there we can configure multiple standby name nodes can be there. Like if my one name standby name node is down, then we can switch to another name node. But this generally doesn't happen. Very it's quite rare. This will happen, right? So these we have already talked about in Hadoop 1.0. MapReduce cluster source management and data processing was all done by the MapReduce itself. And for storage we have used HDFS. But in Hadoop 2.0 we have got the concept of Yarn, which was reduce the task of this cluster resource management, and the only task of the MapReduce was to just data processing, right? So it has reduced a lot of work from this. So again, this is the difference between MR1 and MR2. So we have already talked about all those things. Now, can you just whatever we have discussed,
Mhm.
can you answer this? Yarn was developed to overcome the following disadvantage in Hadoop 1.0 MapReduce single point of failure of name node. Why Yarn was introduced? If you remember, only one version can be run in classic MapReduce, or too much on the job. Job tracker is resource manager, you can say. Why Yarn was introduced? Remember, I just shown you here itself, right?
Mhm.
Because most of the task in Hadoop 1.0, MapReduce was doing, like it was data processing as well resource cluster resource management. So because of this, it was getting overburdened. So this reduced too much burden on the job tracker, right?
Mhm.
It reduced a lot of burden from the job tracker.
Okay.
Then in Yarn, the functionality of job tracker. Job tracker के दो काम थे. That has been replaced by which of the following Yarn features? Resource management and task monitoring. These two tasks, right?
Mhm.
These were replaced by the Yarn itself. The only task of the MapReduce was just to process it, right? And these two tasks are given by the resource manager, the resource, and per application, and application is mastered for the task monitoring. So these two tasks were taken up by the resource manager, Yarn itself, right?
Okay. Yeah.
In Yarn, which of the following daemons takes care of the containers and the resource utilization by the applications?
Application was the no. Job tracker.
Job tracker is basically applications. In Yarn, which of the following daemons takes care of the containers? Containers का क्या है? Applications master का काम है ना? And the use by the applications.
Application master. Okay.
Okay. Can we run MRV1 jobs in yarn enabled? Yani ki MRV yarn enabled means MRV2 that we are using like Hadoop version 2. So हम MRV यानी कि what it means is like Hadoop 1 के job हम Hadoop 2 में run करा सकते हैं.
Can we run MRV job?
Yes. Generally, what happens like whenever we are coming up with the upgradations, so it doesn't happen very early that okay whenever let's say Hadoop version 2 is coming, so whatever the Hadoop version 1 was coming running, we are able to do it through Hadoop version 2 also, right?
Yeah.
It generally happens, right? Like even if let's say whatever, let me give you an example. Let's say Windows 10 is replaced by Windows 11. So whatever we were doing as a part of Windows 10 or even 8, we are able to do in 11 also, right? But it doesn't happen that okay we have come up with in Windows 11, so whatever we were doing as a part of Windows 10, now those things we won't be able to do in Windows 11 because like even some of the peoples they are still using Hadoop 1, they have not migrated to Hadoop 2 irrespective of any reason, but they should be able to do it, right? Because what happens is like even if we are like doing some sort of work on Hadoop 1 and we are adopting to Hadoop 2, so it doesn't mean that whatever we are doing as a part of Hadoop 1 that this is going to be stopped. We should be able to run the same jobs that Hadoop version 1 jobs were running in Hadoop 2 itself, right? Yes. So as I told you, this is one example that we should understand to understand the MapReduce very clearly. So this is how it happens actually. So this is a real very good example to understand it. Simple as well as good example. So what we are doing is like say we have some input. This is just for example, we have taken only 3 lines of code, right? But in real scenario, this file can be in GBs, right? You can test it. Dear beer river, car river, dear car beer. So what we are going to do is we have to count the occurrence of each word. Like dear is there. This is dear is different, but it should be D double ER, right? Dear beer river, car river. So we have got 2 rivers are there, 3 cars are there, 2 beer and 2 deer, right?
Yeah, 3 cars, 2 deers, and 2 beer, 2 river. Yeah.
Just for understanding, we are taking. So basically, what we are doing, we have just put this as input to my system. This is my input. So I'm taking that this input, and this input is of 128 MB, right? So that's why it is containing 3 input splits, right? So this had been split it into 3 input splits. So deer, beer, river, car, river, deer, car, beer. But in real scenario, this is going to be the part of one split only because we are having 128 MB, right? So 128 MB of text is going to be very huge in real scenarios. But just for understanding, we are taking it. So basically how it does is basically this splitting is as it will go to the splitting is
it's 128 MB.
Yeah, it's 128 MB. It's the same as I told you. It's the same of the block size, right? There is very small difference that I'll tell you what is that. But as I told you, just for now, you can take it as my input split and block is same, right? We'll come to this point just in next 5 minutes, right? So
okay,
as I told you, so input split is going to take this whole line and converting into key value pair. So it's how it takes this as the key value pair. So this takes this the starting point basically as my key. So for this key is going to be, let's say, 0, comma, dear beer river, likewise this. So this key one is going to be 0 and v1 is going to be whole line. And the next key is going to be the number of characters with /n. It means new line character. So 4 plus 4, 4 plus 4 plus 8, 8 plus 5, 8 plus 6, 8 plus 5, 13, 14, 15, and 16. So this is in this line, total 16 characters are there, including spaces also, right? So 4 plus 5, 5 plus 5, 10, 10 plus 5, 15, and this new line character 16. So next key will be start from 17, comma this line, then again whatever is going to be. So in this way my key value pair is going to be generated. This is going to be internal, right? We don't have to do anything. Just for understanding, I'm telling you, right?
Okay.
Understood? So now once I got this split, so split is going to be taken as key1 v1, because when it goes to the mapper always takes input in the form of key value pair, as I told you, right? So when we are going to give it to the mapper will take the data in the form of key value pairs. That's why the splitter is automatically going to distribute my data in the form of key value pair, right? Then what mapper code, because mapper code we have written. So what we have done is, now in mapper code, what we have done is, like, we are taking each line, means value pair. We are taking value, right? We took this value, yani ki whole line, and I am converting, basically I'm just taking word by word, because I have to count the occurrence of each word. So I'm taking the key as my word and assigning each word 1. I'm not seeing like whether if it is having some duplicates, I'm not bothering about at this point of time. I'm just like, whenever I'm just reading a line, wherever I'm finding a space, because it's a space delimited, right? My input is space delimited. So I'm taking the space is delimited. I'm just saying, okay, wherever I'm getting a space, so I'm taking that as a key and value as 1. So here my key is this, and this is my value. Key value, key value, key value, key value, likewise. So my same code is going to apply to all the splits, right? So my mapper input is key value pair and my mapper output is list of key value pairs, because here we have got the list of keys and list of values, list of keys and list of values, list of keys and list of values, right? Tell me, understood here at this point? Clear?
This one is occurrence, right? B, 1 is what? 1 is occurrence.
Yeah, this is the occurrence of each word. Like, we are not counting like how many times this deer is coming in this line. Maybe here we are just taking like car. Here 2 times are there. If I can use it car comma 2 also, right?
Yeah.
But what I have written as the code for mapper, because I'll tell you why we have not used it later, but for now, because this is optimized version, we can do it here itself. But what is going to happen is, it will be like it is easy to implement, right? Because every time we let's say here only 2 cars are there. Let me just give you here itself. But let's say, as I know, my input split is having, let's say, 128 MB file, right? And in 128 MB we can have billions of words can be there, billions of. And if in billions of words, let's say I'm just having 1 million words are repeated once, 1 billion. So 1 million time it has to go back and check each and every time. It has to check it. And then let's say for car one, and then it is again going to check, okay, where there was any car, was there? Yes, it was. Then it is going to do 2. Then let's say after 100 words, again we come up with a new car. Then it will go back, check each and every word and see the car is there. Yes, it is there. Then it will, so if let's say 1 million words are there, so 1 million time it has to do the looping. So you can imagine what is going to be the burden on this. So it is going to take huge amount of time. So why we are using MapReduce? We are using MapReduce to improve the performance, not to degrade it, right? So that's why we are just putting it as 1 1 1 1. This is our optimized version of coding.
Okay.
Yeah. So then this is list of k2 comma v2 is going to be my output of my this mapper. Then it will go to the reducer. Now before going to the reducer, as we are having multiple splits are there, because again reducer takes the data in the form of key value pair, right? It also takes the data in the form of key value pair. So what we are doing is we are also doing a shuffling. Shuffling is a very expensive process, and but if we are not doing the shuffling, then reducing is going to take a lot of time. So to reduce the burden on the reducer side, we are implementing this shuffling part. So shuffling is basically doing, what we are doing is we are taking the K2, means key 2, which we got from output of mapper, and we are combining the list of values. So K2 comma list of values. So like beer, one beer is coming from here and one beer is coming from here, right? So 1 comma 1. Then car, 2 from here, 1 from here. Here same way and reverse same way. So here what we have done is like we have shuffled we did the shuffling in all the our input splits. And finally in reducer we are just for each key we are just adding these values, we are just combining these values, right? So if you think like if we are not using this shuffling part and this shuffling part has to be done by the reducer itself, then shuffling is again going to happen, but it will take more time, right? Because reducer generally used to work on it used to get the data from each of the mapper and combine it to give it to the reducer. So in this way, we are going to get beer 2, car 2, deer 2, and river 2, and this will be my final output as beer 2, car 3, deer 2, river 2. So this is list of K3 comma V3. So this is how we generally perform our MapReduce task.
Okay.
Any questions, any queries so far? Please let me know.
No, it's clear for me, but I don't know how it works in real time. But yeah, I know in future we're gonna learn, but
Yeah, okay. So
why
basically,
everything
yeah, so
imagination.
basically this is how the MapReduce works. Like map always takes value in the form of key value pair. So map gets the input as key1 v1, it produces the output as k2 comma v2. Then it goes to the reducer. Before going to the reducer, shuffling is going to happen and get the output as k2 comma list of v2s, and finally list of k3 comma v3 as my output, right?
Okay.
So now input to a mapper is in the form of a flat file, key value pair, only strings, or all of the above.
Key value pair.
Right. Because always mapper takes the value in the form of key value pair. Now, sorry, as I told you, input data. So a block is a physical division of my data, but input split is a logical division of my data, right? How it works? Because this is physical division means like whenever we are going to have physical in physical memory, let's say I'm writing, hi, how are you? So hi, are you? Let's say this is my block boundary. Let's say these were five, let's say this is my 1, 2, 3, 4, 5 statements are there, right? So what happens is there, before my fifth statement completely finishes, before that my block boundary finishes. So in my physical boundary, whenever my 128 MB finishes, it is not going to allow a single character to be added or to be stored to that physical block of my data, right?
Mm-hmm.
Say my last statement was, hi, how are you? So how are and space you, let's say you, in my physical boundary, let's say it just come as y, ou left. It should went to this part, right?
Mm-hmm.
So when I'm doing my processing, so basically these are going to be processed as two different words, y and ou. So it is going to impact my results, right?
Yes.
So in input splits, what happens is input splits basically a logical boundary of our, so they can neatly fit. The logical records are the lines that cross the boundary of the block. So basically what it happens is my input split is stretches its boundary to get this whole sentence into this logical split, right? So
Mm-hmm.
we should get the correct results. So this is the only difference, right, between input split and HDFS block location. So block is physical division, where wherever my 128 MB finishes, it is not going to allow a single byte of data, right? But split can stretch its boundaries to get the complete logical record into the input splits, right?
Mm-hmm.
Now, how this, as we have already input data is there, so multiple nodes are there. So my data is going to be distributed across multiple nodes. Then mapper task is going to be introduced. Then after mapper intermediate, results are going to be calculated in the form of shuffling. When the shuffling is going to happen, and finally the result will move to the reducer itself, and we are going to get the reducer's output as our final output, right? This is how we,
Okay.
this is how we generally work. So now MapReduce programming model provides a way for reducers to communicate with each other.
Yeah, please provide a way for reducers to. Yes.
Are reducers talk to each other? No, they actually, each reducer runs independent of each other, right?
Oh no.
Yeah, because reducers generally you are going to have only a single reducer in most of the cases. But if multiple tasks are running, so for multiple tasks, multiple reducers will be there, but they are going to work in isolation. They are not going to talk to each other, right?
Okay.
But particular application, we can have multiple mapper tasks can be there. Those multiple tasks are going to be assigned to a single reducer. But if my multiple applications are running on my cluster, so there are going to be multiple reducers can be there, but those are going to be for different independent applications, right?
Okay.
That's fine.
Why is this?
Okay. So another important point that we can talk about is combiners and partitioners, just for our understanding. So sometimes what happens is that, like, there is another, like we can combine the combiners. We generally used to call them as mini reducers in the map phase. So the only thing is like combiners are going to be worked as a mini reducers within the map phase itself, right? And partitioners are basically just to like if we want to make our system more performant, so we can also use the partitioners, because partitions play a very vital role in optimization process itself. So basically what we does is like combiners are known as mini reducers, because they are going to before moving their load to the further to reducers, they reduce it, the result, so that uh, the burden on the reducer can also get reduced. That's why we call it as a local reducer. So just for an example, let's say if we have got these two blocks of data is there, we were using the word count here. Let's say if we are using the character count, right? So this block of data is going to be run on the mapper. Then like same that we have, mapper is going to get the value in the key value pair. These are the key and the values. Then if we are not using the combiner here, so what the shuffler has to do is like shuffler has to do b1 comma 1 from here. So here we are going to have, instead of having b comma 2 itself here, we should have b1 comma 1 and then b1 from here itself. Same for c, d, e, likewise. But here what we did is like at the mapper side itself, we have combined this result, right? So after mapper's output within, before moving it to the shuffle, we have added one more, combiner, added one more step, so which is reducing the burden on this shuffle also, because if it has to shuffle, so here it has to go two times, it has to read b1 comma 1, d1 comma 1, d1 comma 1, a1 comma 1, likewise, right? But now what shuffle is doing, just reading b2 from here and 1 from here. So you can think about this. This is very simple example. Let's say we have got 100 times a particular output is, or 100 times one particular character is getting repeated. So how many times this shuffle has to do the shuffling, right? And as I told you, shuffling is one of the the costliest process that we have, because in real time itself, the main the problem still we are facing is with this shuffling. So we have to reduce this shuffle as much as possible. It's we cannot uh, remove it, but we can reduce it. So we always try to reduce this process, right? So because of this, you can see the performance is going to be increased a lot. So, but this is not going to, combiner is not going to work uh, in cases where we don't have, where duplicates are not there, right? Because combiner can only work if these are the unique ones, all are unique ones. So there is no point of putting the combiner in between, because combiner again, it is not going to help a lot. So combiner we have to use whenever we are having a lot of duplicates, right?
So this combiner, this mapper and all, it's a background process, or do we are going to select and then and are we is kind of
No,
option
no.
we gonna
This is what we have to do as a part of programming, right? The only thing we have to do is mapper and reducer code. These two files we have to write. Rest of the things like splitting the files and finally storing the files, that all being done by the system itself. The
all
only
right.
thing is because mapper is the logic that we have to implement, and that's why it has to be written by us,
How
right?
we know it is the mapper is working with the combiner and then the shuffling?
Because when we are going to work on the MapReduce as the name is specified, when we are working with
Mm-hmm.
the MapReduce itself or Hadoop. So Hadoop internally, everything process in the form of map and reduce only. So whenever we are let's say processing anything, so automatically it will pick the get the input splits.
Mm-hmm.
Then on each input split is going to apply the mapper logic, and then once mapper's output is going to be there, automatically it will apply, send it to the reducer, and finally my reducer is going to give the output. But what my reducer is doing, what my mapper is doing, that is going to be specific to the problem, right? And that code we
Mhm.
have to write, right? So the
Okay.
logic is, this is what we are going to write the logic. Here, you don't need to take care of all those things, because now the processing is, we have to do either using, SQL, PySpark. So that is not tough as compared to this mapper and reducer ones. So these are, I'm just telling you for, for the background itself, to give you the background how we generally
Okay.
work it, right? But
Mhm.
in our scenario, nowadays we are not using MapReduce at all. Yeah, in somewhere we are storing the data in Hadoop, but,
Mhm.
and that is only where we are not using any of the cloud technologies. Apart from this, as I told you, one of my friend who is working in TCS in US itself, is
Mhm.
working on this, this Hive part. So they are still storing everything in HDFS, and for processing they are using this Hive itself, right?
All right.
But this is, I must say, this is very, very, rare as of now. Like, I think, I don't have the exact data, but yeah, it should not be going to be more than 10%.
Okay.
Yeah.
Mhm.
So combiner works as our mapper level, right?
Mhm.
Yeah. So basically, partitioner, how it works is, so if we are going to do the partition, so based on the partition, like if we have identified some sort of partitioning key, so the what the reducer will do is going to do is like, with the help of partition, we can create multiple reducers, so that similar key is going to go for the same reducer, right? So even in case of, so let's say I have to find out, let's say I got, let's say, last 10 years of data, weather forecasting data I wanted to process, and that I have to store as my final output in the form of months. In the last 10 years, what was my January's data, what was my February data. So this month of the year are going to be my partition keys. So based on, so this is going to be partition key. So in this case, my 12 reducers are going to be there. So produce me 12 output files, right? So this is how it happens. Got my point? For the part, so like, partition, so that's why I'm telling you, like, and whenever you have to get the data back, let's say I have to, if I have not used any of the like I have not stored my data in the form of different partitions. So if I have to query, let's say, May data, so it is going to, search for all the all the months data instead of just May data. But if I have to get, if I'm having my reducers output as different, partition keys as month, so in that case, if I'm querying the data from HDFS or from the, cloud, or from wherever my data is stored, so I'm just going to give, let's say, for SQL, I'm saying select star from table name where my month equal to May. So it is going to skip all those 11 months. Only it will fetch the data from the May month. So it will be faster. And if we have not used this concept, then definitely it has to go to each every month, find out the May data, and then it is going to, get the data. So it is going to be very, bad query. So to make it performant, we generally, what we do is, even if we don't have the data, we used to partition the data on that partition key, and then we are going to do that. So this similar way we have to do it. This thing I've already done. So yeah. Okay. We have already done this, right? This thing we have already done. This thing. Okay. So now we are going to, just talk about some of the fundamentals of our warehouse. You must have, uh, you must be having idea on that. If not, then you should have it. So just for this, so to understand all this. So we have already talked about this OLTP and OLAP in my first session itself. So just to rewind all these things, because now onwards we'll be using these things, or directly or indirectly we have to use all these.
Okay. Focus on day-to-day operations like processing, sale, or ATM withdrawal, online transaction processing, analytical processing.
Yeah. So OLTP as the online transaction process. So basically, it focuses mainly on what we are doing on daily real-time operations, day-to-day basis. Like we are placing some sort of orders, focusing on what high transaction volumes. Wherever as our OLAP is mainly online and analytical processing. This is mainly for doing some sort of historical analysis whenever we are very huge amount of data is there. So to make the decisions, like say we have to do some sort of analyzing monthly sales trends, and when so these kind of things we generally use this OLAP. So if I talk about the differences, so say like online transaction processing is mainly, it's a day-to-day the operations that we are doing, but OLAP is going to be whenever we have to do some sort of historical analysis. And in OLAP, uh, if I talk about what kind of data types that we are going to have, so it's going to be some sort of aggregated data. Generally, let's say gold layer tables are going to be there, which are having let's say 10 years, 20 years of data, so historical data. But in OLTP, we are generally going to have current detailed information and data that we are going to use. And in OLTP, we generally have got whatever the frequent inserts, updates, or deletes that we are going to do as a part of online transactions. And in OLAP, generally it's going to be very complex, reads, historical data, or the aggregations that we are doing. In online transaction processing, basically the speed, if we talk about like how it is going to processing, so it's going to be in terms of milliseconds. And in OLAP, it's going to be seconds to minutes to even few minutes of data that we are it can take. So if you talk about any of the examples, then like ATM withdrawals, or we are doing any sort of banking transactions that we are doing, those comes under OLTP. And OLAP, it's going to be we have to analyze some sort of sales reports, or you can talk about, let's say, some recommendations, let's say Netflix recommendations, or match analysis that we are doing. And nowadays, like we always, with the help of you know these AI tools, even we can do those analysis at near to real time itself. Then another one is the ETL and ELT. This is another very few people thinks that okay, these are both the terms are same, but they have got differences are there. So we need to understand the difference. Basically, the difference comes in terms of how we are, using these ones. So basically, ETL is extraction, transform, and load. Although ELT is also the same, extract, load, and transform. The only difference is how we are doing it. So basically, in ETL, data is clean and structured before we are loading into the warehouse. So we generally use it traditionally used for on-premise systems. But ELT is a new system that we are using nowadays, as like Snowflake is a ELT, BigQuery is an ELT, or we can say it's a BigQuery we call as, it's a cloud warehouse, right? So raw data is loaded into the warehouse first. So in ELT, what we are doing is we are loading the raw data into the warehouse, and then we are transforming it using our warehouse compute power. So this is, as I told you, it's modern cloud systems. So BigQuery is a cloud, data warehouse. Snowflake is also a cloud data warehouse.
Okay.
So if how we are basically using them and what could be the key differences that we need to understand. So if we talk about the speed, so ELT is much faster for ingestion because data is not processed upfront, right? Because we are just loading the data first, and then we are processing from the warehouse own compute power, and based on that. So nowadays, like if you see, BigQuery is one of the the fastest analysis tool that we have. Same is for like BigQuery is from GCP, but then we have got Redshift from AWS and Synapse from the Azure. But if we have to compare the speeds out of these three, so because I've worked on all three, so uh, I've just queried 5 terabytes of data. So like BigQuery is able to give the result in few seconds, even in 4 to 5 seconds. So this way, it's quite fast. And if we talk about the where we have to use it, so ETL is mainly better when we are working with sensitive or PII data, because here we have to clean and structure data before loading into the warehouse. So that's why it's required compliances or masking before loading. But ETL is going to be best because in ELT what we are doing is we are directly loading the data. I mean, we are not doing any sort of, so whatever the raw data is there, we are loading it into the warehouse itself, and then we are processing it. So ELT is going to be best for large volumes of data where we have to do some sort of real-time analytics. And so this is how happens. And another thing is like in ETL, as I told you, it's for processing. It happens in a separate processing engine. But ELT, it is there in the target system itself. So wherever we have stored it, so there itself we are going to process it. So these are the some of the differences that we should know. Then
Okay.
if you have know about this, different schemas are there. So basically, we have got star and snowflake schemas there, right? So within each, we are having some fact tables and dimension tables. So fact tables basically contains quantitative metrics like measures in terms of numerical, quantifiable data, business events, sales amounts, high volume of data. While the dimension tables basically, they stores the data about like what the fact table contains, like who, what, and where, and when this data has been produced, like product name, customer details, date, store location. These kind of information are going to be part of dimension tables. And whatever the quantitative analysis data is there for those dimension tables, that comes under this fact tables. So
Okay.
And then we have, as I told you, we have got this schema design. So we are having like star versus snowflake. This question is generally going to be asked, like in any of the interviews. This question, like for a data engineer role, this question is a must. Like for me, this is a must ask question, because we should understand the difference between star and snowflake schema, and when we have to use which one, which is going to be used in which scenario, we have to use which one. So if we know star and snowflake schema, then we should also have got the idea about what is a fact table, what are the dimension table, because both my schemas contains this, uh, fact and dimension table. So within the star schema, basically we have got fact table which is at the center, and all the dimension tables which are denormalized tables are connected to this fact table. So these are denormalized tables, so that's why they are optimized for fast queries. So whenever we have to use any of the BI tools like Power BI or Tableau, we have to do any sort of we have to publish any dashboards on top of it. So we can use this, and as you have already so you have also worked in BI, Power BI, right? What I remember, right? So
I was on the meeting. Yes.
yeah. So you must have used this star schema.
Mm-hmm.
So basically, whenever we need optimized results, fast queries in BI tools, so there we are going to use star schema because it is faster. Uh, the architecture is quite easy to implement, and as the tables are denormalized, so there are less number of tables, no normalizations are there. But when it goes to the snowflake, so it's the same, the extension of my star schema, where okay, so this is an extension of star schema where dimensions are normalized into multiple related tables, and all those related tables, those are going to be the normalized tables. So the basically it becomes quite complex. Schema becomes quite complex, but if we talk about the storage part, so it becomes optimized from the storage perspective, because all the dimension tables in my snowflake, they becomes normalized tables.
Mm-hmm.
So if I talk about generally we need to have, like in star schema, tables are denormalized. In snowflake we have got normalized. So if we have got denormalized tables, so the, the speed is going to be faster, as we are going to have very fewer joins are going to be there. But in snowflake it's going to be more, and it's going to be slower. If we talk about structure level, so it's simple, and a single level structure is there. But in snowflake we have got dimension to dimension tables. Label hierarchies are going to be there. But if we talk about the redundancy, data redundancy, so in star schema it's going to be quite redundant data is going to be there. But snowflake, as the data is tables are getting normalized, so we are going to have very low redundancy. And, star schema, as it's easy to read, and it's quite tough to update it. So it's easy to maintain, but snowflake is again it's easy to update, but it's very hard. So again, it depends on the use case where we have to use it. So wherever you need simple, faster reporting, example where we have to work on small to medium scale, data warehouses, we generally use star schemas. And Snowflake is going to be used where we need highly structured data with significant, label, multi-level hierarchies are there, and complex schema is there. There we are going to use this Snowflake, right? So this was all about some of the key key concepts that we have to keep. So from next class, we are going to work on Databricks, right? As,
Mhm.
as I'm assuming that you know SQL, right? And Python.
Yes. Yes.
Okay. So by the time, what you can do is you can brush up on some of the the important concepts in SQL. Python, I don't say that you have to go through because uh, Python mainly going to be used where we have to when we are going to build the basically the whole architecture we have to, or the whole pipeline we have to build or architecture
Mhm.
to design. But I think with the introduction of this DLT as well as we are having the concept of PySpark, that is not required because if we have to build some sort of proper different system we have to build, and that should be that needs to be configurable. There we are going to use that need to be have different source of data need to be captured. So that is different, architecture and process that we have to build. But that generally most of the organizations what they are doing is like they generally build their pipeline based on the requirement itself. That we can go with the notebook concept where we are going to get the data ingestion, and based on that, if we are working on the Databricks itself, so there we are going to utilize services from Databricks itself, and if we have to use other services, as I told you, so we are going to use Azure. For let's say orchestration, we are going to use Azure Data Factory. Storage, we are going to use Azure. Gen 2. So those things we will be, exploring in next classes, right?
Okay.
But before that, if you just go through this
SQL concepts.
concepts, because in Databricks we have to use that. But if we talk about Azure ADF side, so
Mm-hmm.
it's basically no code configurations are there. There we have to only need to make some sort of connections, link services, get the data in the source and the target, and we just need to build the pipeline and trigger it. So automatically it will do everything for you in background. But what I want is like you should be ready with both the concepts, right? Like
Yeah, yeah, correct.
because it's not going to be the case that every time you have to do it through ADF and Azure within the Azure itself. So I want to make it this is, you should be able to adapt to different technologies, right?
Yeah.
Because what I feel is like future is going to be the single unified things as Databricks is there. But yeah, even like I'm not saying like Azure is not doing good. They are even, but they have made it or totally no code. We are having as a part of even in DLT pipelines also. But there we have to write some sort of code. But the thing is like when we are dependent on no code, so there are some sort of dependencies that we have to follow, right? We cannot We cannot make changes as our expectations. But when we are doing it through coding itself, so you can do it whatever you want, right?
Mm-hmm.
So everything has got pros and cons.
All right.
Yeah. So
So can you please share me this whole
yeah,
uh,
I'll
PP?
share you all the PPTs.
So if I have any questions in any if I have questions, I can text you, right?
Yeah. Anytime you can text me anytime. And
Okay.
if
Mm-hmm.
next, actually, I'll try to make a class in weekday. Also, if possible, I'll check because there are a lot of things which are going on, and I also have a uh, wedding as well as I'm having a my event is there. My office event is there on next Saturday. So Saturday I won't be able to attend this session. Sunday is fine. Sunday is fine, but Sunday evening will be fine for you, like the same time that we are doing today.
That's fine.
This is going to for next week only. From next time
A
onwards.
bit yearly would be fine, like Sunday. See, like 10:30, I have my son's class. I
What
have to
what
take
time?
him. I mean 10:30 for me. It's already
What time is now?
10:40.
What time is now there?
10:40. Here is 10:42 exactly.
So what time you want it?
So like 5 o'clock, 4:30 would be fine.
Okay,
So
okay.
anytime.
Okay, so fine,
Bit
no worries.
yearly would be fine because I
Yeah,
have
then
to.
that's fine. That's fine. You are saying like instead of 6 o'clock IST, you want it at 4 o'clock IST, right?
Yes.
Yeah, that's fine. That's fine. Okay. So I'll try if I can make it in the weekday itself, if possible. Otherwise, we'll have the class on Sunday, right?
Yeah, if it is weekdays, I cannot attend in evenings because that's going to be my morning, right?
Yes.
Because I can attend in your morning. I can attend anytime AM for me for you because that's going to be evening for me. If it is in the morning, I have my kids' school, so I have to make them ready.
Okay.
So yeah,
So
if it
if
is
it
in the
is
morning, that is fine. When it would be fine means until 9 a.m. Until 9 a.m. I'll be busy. After that, you can make sessions like
no,
9 a.m.
definitely
Yeah.
it's not going to be 9 a.m. because generally on weekdays I'm having my call at sometimes it goes back to 11 p.m. So it will be around 1:30 for you, right?
Mm-hmm. Yeah, that is fine for me then.
Yeah, but it's going to be very late for me.
Yeah.
Yeah, but yeah, I try. But if not possible, then definitely next Sunday, right? But
Yeah, if it is
from next
possible, you can instead of taking it for 1.5 hours or 2 hours, you can make it for like 5 to 40 minutes, even 35 minutes like that, and then you can
yeah,
split it up
then that
into
yeah,
three
then that
days.
will
Yeah,
be
if
fine.
that works for you, you can do that.
Yeah.
That is
So let's
fine.
let's let's do it on Sunday, and we'll make it 3 hours, right? Will that be okay? And because that will be having some sort of hands-on, so it will be very exciting also. So,
Okay.
right.
Okay, then start it a little bit early. That would be
Yeah.
fine.
Yeah. And like, what is your system configuration? It should have at least 8 GB of RAM, right? At least, I think 16 GB
16,
is fine.
16 GB.
Yeah, that is fine because sometimes if it is less than that, so
No, no,
yeah,
no. It's recently bought. That's fine. Yeah.
okay, fine.
Okay.
Okay then, thank you.
Thank,
Have
thank you. Don't forget to share me the
yeah,
PPT.
I'll share all those things, right.
Okay. Thank you.
Otherwise, I'll forget. I'll share it, right.
Yeah. That's why.
Okay.
Thank you. Yeah.
Yeah, thank you. Bye bye.
Bye.
repeat to